Thank you. Yes, I will have a short introduction about QKD, things you already know very well, but just to recap. And then I will talk about the project that we are implementing and some recent activities in the project. So just a quick reminder of QKD technology. So it operates over either fiber optics or through space. And it securely shares a secret key between two nodes without using asymmetric crypto. So you could do that with a pre-shared key method, just having generated new unique keys and just copy them in two different places and use them. You don't need asymmetric crypto for that, but to do on-demand connection establishment, you need asymmetric crypto at the moment, either Diffie-Hellman or some kind of other schemes. Those critical steps in the beginning of session establishment will be crackable by quantum computer. And so QKD allows us to use the fragile nature of quantum to do this sharing of secrets with guaranteed detection of eavesdropper. It is detected by detecting very high levels of error percentage, significantly above 50%. And those devices are programmed to be very conservative or skeptical. If they detect very high error noise, they simply don't believe everything they hear. Only when an eavesdropper goes away and the error percentage goes below a certain level, they know that only two ends of the communication know the key. Okay? The key material itself is generated with a true random number generator, quantum RNG. So the key material itself is high quality and guaranteed to be known only to both parties at the end of communication line. This technology is categorized as quantum cryptography technology. Some scientists debate this because it's actually not used to encrypt the data itself. So not in the classical sense what a cryptography does, right? But only shares keys. Nevertheless, you can feed those keys into applications like classical encryptors, let's say an IPsec or a MACsec tunnel. And so, yes, it shares only keys with the IDs. So the users retrieve those keys using specific API. There are a few standards. One of them is very popular, ETSI 014. I will mention that in a moment. Yes, so the users could be any application that uses symmetric keys. Basically, those are just random numbers securely shared between two parties. We got hands on the first QKD pair, as far as I know, in Latvia in 2019. We started to test how to use it, how to deploy it in real infrastructure. That pair of equipment was actually very intolerant to imperfections in optical infrastructure. And we had quite a challenge to deploy it in real infrastructure. But we did it. On the left, you see LVRTC television, mostly television tower. Here, on an island in Daugava, not very far from here. By the way, it's highest tower in Europe. There is a data center, and we placed QKD equipment there and ran this QKD pair through 33 kilometers of real optical infrastructure. The pair that we used was was provided with data that it operates up until 50 kilometers. I know this is very far from world records, but nevertheless, it gave us confidence that we know how to operate it in real environment, we know how to use it. And speaking about how to use it, we could just retrieve the keys and call it a success, but we went further. We took 2 Linux IPsec machines as IPsec gateways. Since QKD devices are usually called in pairs Alice and Bob, we decided to use Latvian names, I and Brencis, for the encryptors. And we added very simple, actually trivial, key management system onto that, so that one end of the IPsec tunnel, Aya, takes a key from Alice. Taking the key also understands what's the ID of the new key, then passes only the ID to Brencis over classical communications channel, and then Brencis retrieves the same key from Bob. So only the key ID is passed over classical channel, even if it's eavesdropped or hacked later, doesn't reveal the key itself. And then I and Brencis enforced these quantum keys for IPsec encryption. And of course, we added 2 subnets as users implementing a typical site-to-site VPN, just using quantum keys. And so we demonstrated a complete quantum-resistant encrypted channel between 2 sites. And that also gave us confidence that we really understand how to use this technology. And so the main topic of this talk is to talk about this project. It started in 2023, and the goal is to build the first national quantum communication infrastructure, basically the first QKD network. It is a rather large project, and there are 4 partners. The leading partner is the one I am representing today, Latvian State Radio and Television Center. Yes, this organization really provides broadcast infrastructure and actually is already 100 years old. This organization started during the first independence period in 1920s, really by raising radio towers, building broadcast infrastructure. But nowadays, this organization is one of the leading network, data center, and cybersecurity providers in Latvia, probably in the Baltics as well, but mostly to government. Then another partner is Electronic Communications Office. That is basically the organization that monitors radio frequency usage in Latvia and really deals with it. They are here in this project to test QKD compatibility with mobile infrastructure, testing communications with QKD encryption between mobile base stations and so on, Wi-Fi, Internet of Things. Then we have a scientific partner, Institute of Mathematics Computer Science at University of Latvia. They are very good at crypto theory, and also they took on themselves part to discover how to implement the new PQC algorithms. Although some people say that they replace QKD, they don't actually. If you would like to talk about it, please raise questions. Let's talk. But what we are looking for is what Euro QCI community is looking for hybrid solutions where QKD and PQC come together to form increased security communication solutions. And then we have a commercial partner. TET is one of the leading commercial network operators in Latvia. They took in this project a part where they test application of QKD in two industries that probably would like to use increased security. This is finance and medical industries. And they have done their part, tested how to use it in their specific circumstances. Okay, so this is the project to build a Latvian national QCI. There are other projects throughout Europe. Almost all European Union countries develop their own national QCI. Some of the countries have done it already for multiple years and are really ahead of us, like Netherlands, Germany, Spain. Poland has huge QKD network. But some countries are still considering it. So just a few news, so how we are doing, how our equipment performs. So actually we have an interesting situation as most European countries develop their national QCIs using single vendor equipment. We have a situation, well, we didn't want that, you know, in the meaning that we didn't plan for that. But two of our partners have a Swiss company, ID Quantique equipment, and we have Toshiba equipment. You know, those of you who know that crypto technologies much easier click in place when you use single vendor solutions, much harder to integrate multiple vendor solutions. But we have this, I think this is a silver lining around the cloud. Now we have a possibility to understand how to integrate heterogeneous manufacturer networks. And we are doing that in a moment about this. So those are early experiments we did last summer and autumn. So just a short summary, the equipment performs very well, actually even better than promised in the data sheets. When we got the equipment, we already deployed in lab environment, but using real optical lines, 17 kilometers, we deployed a running complete QKD network with manufacturer-supplied KMS. And this is one of those situations when you take from one manufacturer and they integrate out of the box. But nevertheless, this is probably the first redundant multi-node QKD network back then. Toshiba equipment is very easy to monitor, uses SNMP, syslog for push, and we integrated it with Latvian-made Zabbix monitoring system, which is also very popular around the world. And then we started integrating these QKD devices with the real encryptors. And we started with FortiGate. Our partners used Cisco and Juniper. And we first integrated those encryptors with the KME simulator. I'm going to talk about this in a moment. Then with the actual Toshiba KMEs. Now, the KME simulator first, because the encryptor and the Toshiba QKD device, they are basically black boxes. There's very little information we can diagnose in depth. There are standard metrics we can get from them, but when something doesn't work, well, we can only escalate to manufacturer. But we wanted to understand how this works actually between them, how the talk between them works. So that's one unexpected result developing our KME simulator. We were able to exactly see how the requests are formed, what are the crypto algorithms they use to establish HTTPS, and so on. So yes, that was very beneficial to understand how this clicks together. And then, yes, integrated with the Toshiba, also integrated our own certificates. Basically, we implemented a simple public key infrastructure ready to be used for multi-partner establishments. You know, all this work comes down to this one line in an encryptor, QKD, yes. Okay, that's how we know it works. Of course, other signs as well, but, you know, 2 words, but so much work behind it. So yes, the KME simulator. Now, when we started the project, we saw that there is sort of vacuum in application development toolkit and infrastructure. Basically, if you want to develop your QKD user, you need to have access to real QKD devices. Those devices are very expensive and are not easy to operate. So yes, I must say, in cooperation with the University of Latvia, our bright students came to rescue. They developed this KME simulator. Basically, those are 2 Linux Docker containers that come up, and they provide the key service with the ETSI 014 standard the very same way as real QKD devices do. Okay, so you can use your user according to ETSI standard that is called SAE, Secure Application Entity, and the KME is Key Management Entity. Basically, that's a client and a server for the keys. So you can easily develop your users now just using this QKD simulation. It doesn't simulate the QKD protocol in the way how they exchange keys. They actually do it in a very unsecure, primitive way, but that's not the point. The point is to provide service as the real systems do. So that was very good. And then we went further. We developed a fully functional key management system. And we also published it in open source. To my knowledge, there are only 2 open source KMS systems developed in Europe. This is one of them. It is really a fully functional KMS. It includes 2 very important functions for a real KMS. One is key routing. So being able to have one starting key on one node and pass it through multiple trusted nodes throughout the infrastructure. In the triangle topology, as we see here, there's not much use for key relaying, I guess. Multi-hop is not necessary. From every node, you can get just one hop to the other. But in larger topologies, it is important. And we use classical Dijkstra, shortest path first algorithm for key relaying, which was a surprise for some other European KMS system developers, that we use this fully functional, mature IP routing protocol for keys. And the other function for real KMS is key relay, crypto relay algorithm. So, you know, the result of key synchronizing in QKD is unpredictable. It's not that you say, Alice, okay, take this information and synchronize with quantum effects to the other side. No, the synchronization takes, the protocol works in such a way that the receiver doesn't know which basis to use for spin measuring. The receiver just guesses. Then they later talk about the measurements, and the result is secure bits that form the key. This is very, very simple. It's actually much more complex, but like this, okay? So the result of key synchronization is unpredictable. So imagine that you need to get one key through multiple unpredictable key synchronization links. At first, it even seems theoretically impossible, but there are relay schemes for that. We implemented here in the system BBN hop-by-hop algorithm. I think I must end, but we had a few minutes spare, okay? I will finish soon. Yeah, very good. So now we have a fully functional KMS, home-developed. We can build any topology and experiment it with it how we like. And we also can replace the simulated QKD links by QKD, okay, with real QKD links. And so integrate into this KMS part of the links that are still simulated and part links are already physical QKD devices. So this allows us to build network not adding link to link, but already establishing a KMS, start with simulated links and slowly replacing with real ones. I think this is a quite new approach, but we can do that. That's good. And yes, in this picture, the underscored parts here are the ones that we put in from real infrastructure. So the trusted nodes, the users, real encryptors, IA Brains and Cilda, and simulated and real Toshib devices. Like I said, we use our own keys, public key infrastructure. Okay, so actually, we already have a KMS. We already know how to integrate with real QKD devices. We are very close to actually have built this network. So what we now need is just two things to do, is integrate with other vendor QKD links. And we are in a process of integrating with IDQ devices, and then just complete the network configuration, and we are ready to bring those objects to physical places where they need to be and just run, okay? You probably can hear some optimism and enthusiasm. That's real, honest, because we are very good, very close to that, and we think that the result will be good. Okay, just the last slide, the very fresh news. We were able to push the Toshiba QKD devices to the limits. Manufacturer promises they will work up to 30 decibel attenuation. We ran it on 33, and we run it currently on 140-kilometer line, which has 31 decibels, including dispersion compensation. We need to use that component as well. And perhaps we can go even a few kilometers further. Okay, publication is coming, so if you are wondering how this ends, then stay tuned. This year we end this project, and I think we are going to have very nice news throughout this year towards the end of it. Thank you.